Hello, everyone. Thanks for the introduction. I'm Adi from ETH Zurich, and I'm very happy to be here to present our work, Cassandra, and this was a collaboration with Trevor Carlson from National University of Singapore. All right, first I'm going to just give you a high-level overview of this work. So we have these cryptographic programs that are very interesting for attackers to attack because they use secret keys as inputs, right? So there have been many attacks that use the timing side channels of these programs to extract the secret, right? So many libraries deploy some programming rules called constant time programming that would guarantee that all the timing side channels of the program are independent of the secret inputs of the program. However, we had these speculative execution attacks introduced in 2018 that they basically violate all the assumptions of the constant time programming because they execute unintended paths of the program that are not guaranteed to be constant time. So the goal of our work and many other prior defenses was to strictly enforce the constant time assumptions like sequential execution to ensure that these programs are safe. So the trend of all defenses has been to monitor the program's behavior during the speculation and then see that if there is a leak, they would restrict the speculative execution, right? And this results into very restrictive speculative execution. However, in this work, we propose Cassandra, and we take a step back and ask the question that do these programs even need a speculation, right? So in this work, we believe that no, they don't need the speculation, so we disable the branch prediction and just record and replay the sequential execution of the program. All right, now let's go into details of these crypto programs. So usually these programs encrypt or decrypt the ciphertext and plaintext, and in order to do this, they need a secret key. So they directly work with a secret key. And if some of the timing side channels of the program depend on the secret, then that's bad. I mean, then the attacker can extract the secret. And these timing side channels usually consist of the control flow of the program, the memory access patterns of the program, and the variable time instructions that could have a different timing based on the secret operands, right? So the constant time principles and the constant time programming ensures that all these timing side channels of the program are independent of the secret input, right? But there is an assumption in all the constant time verifiers and the developers that they use constant time programming that the program always executes sequentially. And what does this sequential execution mean, right? So let's look at this simple example that we have a for loop that it iterates 3 times, and it processes a state 1, and then it follows through and then processes a state 2. And this is the sequential execution. This is what you expect from the program, right? You process a state 1 3 times, and then you process a state 2. And all these constant time principles ensure that this execution is independent of the secret. Right? However, a speculative execution in modern CPUs violate this assumption, right? I'm going to just give you one example of what can happen, right? So you have a branch predictor that is called, and you have this loop, and it might mispredict, and it skips the loop totally, and then you process a state 2 transiently, right? And then the CPU realizes that this is not a correct prediction, it aborts, and then it goes to the correct execution, and it does what it's intended to do, right? It processes a state 1 3 times, and now you have a branch predictor that is warmed up with this loop, right? And it might transiently process a state 1 again, right? So this can usually happen. And then it realizes this was a misprediction, and it goes and does the correct thing. And this was just one example that could happen during a speculative execution, right? And this is not guaranteed to be constant time by the standard constant time rules that we currently have in the crypto libraries. So what did defenses do? We have this secret in the CPU, right? Then we start speculating. And until the speculation resolves, we have this speculation window. And all these defenses monitor the secret propagation. And if they detect a transmitter that would leak the secret, they would restrict this execution, right? However, these crypto programs are really hard to mitigate because they directly load the secret non-speculatively, and this can be resulted into extremely restrictive execution in a way that, for example, SPT is one of the prior works that can show up to 59% slowdown, and Prospect is also the state of the art that can show up to 15% slowdown. However, in this work, we say, forget about the speculation. Do we even need speculation? So we explored this design point that we would disable speculation, and we record and replay the sequential execution that we know this is what is guaranteed to be constant time. Let's revisit the exact example that we had, right? So the first step is to record the sequential traces. So this is the trace. The branch is taken 3 times, and then we have a not taken branch, right? Basically, you fall through to the process state 2. And then the next time that we see this branch, we would just replay the same trace, right? So we take it, we take it, we take it, and then not taken, right? So this would ensure that there are no misprediction, and also we are always on the path that the program is intended to be. However, the recording and replaying in a general case has been proven to be challenging because of these 2 reasons. The first challenge is that the sequential control flow of the program can be different based on the program inputs, right? So you can have many possibilities, and it's a bit impractical to generate traces for all possible inputs of the program. And even if you have these sequential traces, they can be huge, that it's a bit impractical to store and communicate them with the CPU, right? However, there are 2 key insights about these constant time crypto programs that could enable using the recording and replaying. So the first insight is that these crypto programs are guaranteed to be independent of the secret inputs, and most of the public inputs are also defined by their standards, so they do not change during the runtime. So basically, most of the branch traces are static with respect to the program inputs. And then the second insight is that most of the cryptographic applications are highly looped, right? So these are loop-intensive programs that you could just detect these repeating patterns and just save that one and then replay this repeating pattern, right? So this enables us to significantly compress the branch traces. So based on these insights, we designed Cassandra, which is a hardware-software co-design. So we do an upfront branch analysis, and we collect branch traces, right? And then we do a compression technique to significantly compress these traces in a way that they could fit in a small component in the CPU. So for branch trace analysis and compression, we have 2 steps, right? The first one is the collecting branch traces, and then we do a compression. And then to do the compression, we need to ask this question that how can we detect these repeating and unknown patterns, right? So you have these huge traces up to 90 million in some applications, and we want to detect these repeating patterns. We explored many domains that they would do this, and one of these interesting domains is DNA sequencing, right? Because they have these large DNA sequences that they want to detect the specific pattern of the nucleotides in this DNA sequence. So one example is DNA k-mers counting. And basically, this technique wants to, as input, it gets the DNA sequence, and it finds the most frequent and the small patterns in the sequence. For example, in this pattern, if we specify the k as 5, for example, looking for the substrings of size 5 in the DNA sequence, this would be the output, right? It would say that this pattern of ACCGT repeats 6 times, right? So this is basically, this is just the only part of the pattern that we need to save. To showcase the effectiveness of this compression, I'm going to just give you one example of this post-quantum cryptographic program, Sphinx Plus. So these are the original traces size that on average is about 3 million, right? And it can go up to 90 million trace sizes, right? And then after our compression, on average, we have traces of size 20, right? And even the maximum trace size is less than 400, right? Which translates into 1 million compression ratio and then an up to 30 million compression rate, right? And on average, for for a large set of the crypto applications, we get to average 20 branch traces of size 20. All right, now we have these branch traces, and we want to use them in the microarchitecture to actually enforce the sequential execution and redirect the fetch based on these traces. So this is a typical CPU design. You have the fetch and decode, and then execution, and then commit, right? So we added a small unit to the front end. It's called branch trace unit, which consists of 3 main components. The first component is the trace cache that basically holds the traces and keeps the progress of the execution through all the traces. And then we have a pattern table that basically has all the exact pieces that we need to use for the next PC to fetch. And also we have a checkpoint table in order to handle interrupts. So if you have an interrupt and you want to resume from the correct place of the branch trace, then you would use this checkpoint table. Right? So what happens when we have a branch, right? So if this branch is part of a non-cryptographic application, which is not the scope of our work, we will just use a normal branch prediction unit. And in the next slide, I would say why this is safe for this design. However, if we have a branch from the crypto code, you would just look up the trace cache and the pattern table, and it would give you the next PC to fetch, right? And then when you are committing this branch, you just update the progress through the trace cache, and also you would update the checkpoint table, so you would always have the valid place that your branch has been before. And in order, we also we have use the prefix points of the x86 to communicate the traces, but I would say look at the paper to see the details that how we do this, right? All right, now I want to discuss the security guarantees that we give with Cassandra. So we have this crypto code that you have a branch, and then you have this leak gadget that could leak a register or a memory, right? And then also we might have a non-crypto code that is executing on the same core, that also has a branch and a leak gadget. But the guarantee that we're looking for to provide in Cassandra is to make sure that this leak gadget, L1, in the crypto code is always on the sequential path of the program, right? So this is the guarantee that we are looking for. So for these 2 scenarios that we are running this branch, that we are executing this branch 1, this is always on the sequential path because we are looking up the sequential traces. Right? So we are always on the sequential path of the branch 1. And also we have this branch 2 that is non-crypto code, and as we said, we are going to use branch prediction for this. However, for these cases, we do an integrity check that if these non-crypto branches are redirecting fetch to a crypto code, we would just stop it, right? We would just stall the fetch until the branch resolves, and we showed that this doesn't really incur that much performance overhead. However, there is one case that we allow speculation, and it might leak memory, but this is out of the scope of non-crypto code, and also CPUs nowadays have some defenses that might be buggy, and there are still many Spectre v2 attacks, but at least, I mean, CPUs have something in place to protect. However, for the scenarios that we protect in Cassandra, a solution is needed, and that's why we designed Cassandra. All right. Now let's look at some performance results. In order to do performance evaluation, we used the Gen5 simulator, and we used the Golden Cove microarchitecture. And also for the workloads, we looked at some widely used crypto libraries and some post-quantum crypto like Kyber and Sphinx Plus. And in this figure, you could see that we have the normalized execution time with respect to the unsafe baseline. So with Cassandra, we get almost an average 2% performance overhead, and in some applications can go to up to 14% performance speed up, right? So we are actually better than the unsafe baseline, right? However, for SPT, which is like a prior work, it can get up to 12% performance slowdown on average, right? And also we showed that even if you want to protect the Spectre v4 and the data speculation, still Cassandra can provide the performance speed up. And also we looked at the Prospect, which is also a state-of-the-art mitigation for crypto code, which is also hardware-software co-design. And we showed that for more complicated programs like curve 25519 that spills the secret to the stack, we can show much better performance than Prospect, right? And also we looked at the power and area impacts of Cassandra, and we showed that even Cassandra can provide some power savings. So because branch tracing is much simpler, right? But we have like 1% area overhead. So basically in Cassandra, we designed the new defense for constant time crypto that eliminates the attack surface for Spectre. And we showed that we provide performance speed up and with negligible area overhead. Thanks for your attention. I will take questions.